Here's a special Newton's second law problem called the elevator problem. So with the elevator problem, we have you step into an elevator on the ground floor of a tall building. Inside, you find a scale, weirdly. So you decide to stand on it for the duration of your ride to the top floor. If your mass is 70 kilograms, find A, the reading on the scale in kilograms as the elevator accelerates upward at a rate of 4 meters per second squared. B, the reading on the scale in kilograms as the elevator is moving at a constant velocity in the middle of the ride. C, the reading on the scale in kilograms as the elevator slows to a stop at the top of the building at a rate of 4 meters per second squared. So for something like this, what's happening here is those accelerations are causing a change in how you feel, which we call that the normal force. So if you've ever done this, you probably felt this before. If you get into the elevator at the ground floor and you start accelerating upward, you feel heavy, right? And the reason for that is your body is at the bottom on the ground floor and your body has inertia. So you are staying at rest. Now that bottom of the elevator starts accelerating upward and kind of pushes on you because your body has inertia and you're kind of pressed into the floor. So since you're pressed into the floor, the normal force increases, which then causes that acceleration upward. So because the normal force is increasing, you feel heavier. Now, when we're moving at constant velocity, we know that our forces are balanced because there's no acceleration. And then for part C, when you get to the top floor, you're moving upward. And again, your body has inertia. So a body in motion stays in motion. So it's almost like your body wants to stay in motion upward, but then that elevator starts slowing down. So the floor kind of starts almost falling out from underneath you, and the floor is pressing on you less than you're used to. And so that's why you feel lighter at the top. All right, but we'll do it with math as well to show you guys what's happening. So for part A, first and foremost, we want to draw a free body diagram. So our free body diagram is going to look the same pretty much for every single step of this problem, but the normal force will be changing. And that will be what's causing the acceleration here. Remember, the normal force is just the force of the ground of the elevator on your body. And anytime they say the scale reading, so the reading on the scale, that's what we want to know, they're talking about the normal force, all right? Because the normal force is what the scale is actually going to show. It doesn't actually show your force of gravity. It does when you're at rest, because when you're at rest, we know force of gravity equals normal force. But if there's an acceleration involved, or say you're pushing down on that scale, the more you push on the scale, the higher the scale reading. So it's the force of the scale back on your hand. Okay, that's your normal force, the reading on the scale. So drawing a free body diagram for part A, we have the force of gravity down and we have the normal force up. So we know that the elevator is accelerating upward at a rate of 4 meters per second squared. So I'm going to call up positive because that's my direction of acceleration. So for part A, I get net force is equal to mass times acceleration. The net force, the normal force will be positive here. So normal force minus the force of gravity equals mass times acceleration. Solving for normal force, because we want scale reading here, that equals mass times acceleration plus the force of gravity, which we know is mass times the acceleration of gravity. So now we can plug in our numbers here. We get normal force is equal to mass, which was 70 kilograms, times the acceleration, which was 4 meters per second squared, plus the mass, 70 kilograms, times the acceleration of gravity, 9.8 meters per second squared. All right, so we get 70 times 4 plus the quantity 70 times 9.8. We get 966. Now this is the normal force, or the weight that you feel when that elevator is accelerating upward. But we want the mass reading on the scale. So what we need to do here is it's just going to be this number divided by 9.8, because we know to go from weight to mass, we need to divide by 9.8 because force of gravity is mass times that acceleration of gravity. So to find mass, it's going to be weight divided by the acceleration of gravity. So this will be your apparent weight as you're going up. All right, so if we divide this number by 9.8, mass, and I'm going to say apparent, is equal to 966 newtons divided by 9.8 meters per second squared. And so we get 98.57 kilograms, sorry. So notice how this is a larger number, right? And again, it's a larger number because we're accelerating upwards. So this normal force has to be bigger than the force of gravity because we know acceleration is in the direction of that unbalanced force. So that's why you feel heavier at the bottom of that path when you're in an upwards elevator. Now for part B, we want to know the scale reading as the elevator is moving at a constant velocity in the middle of the ride. Now, we don't even really have to do a calculation for this one. If we draw a free body diagram, again, it's going to be the same free body diagram. So force of gravity down, normal force up. But remember, constant velocity equals no acceleration. So since acceleration equals 0, then forces are balanced because we know net force is equal to mass times acceleration. So here net force equals 0. So because of that, the normal force, if I'm calling up positive still, minus the force of gravity equals 0, and therefore normal force is equal to the force of gravity. So because those things are equal, we know that the scale reading will just equal the mass of the person. So it'll be a mass of 70 kilograms. So that's why you start feeling normal in the middle of that elevator ride, because there's no more acceleration. You don't feel it when you don't have an acceleration. The acceleration is this exciting part in things like elevator rides and roller coasters. And then last but not least, for part C, we have the reading on the scale in kilograms as the elevator slows to a stop at the top of the building at a rate of 4 meters per second squared. So here for part C, we again have the same free body diagram, force of gravity down, normal force up, but now we're slowing to a stop. So if my velocity is upward and I'm slowing down, that means that the acceleration has to be downward, because remember, when we slow down, our velocity and our acceleration are pointed in opposite directions. So my acceleration is downward. We can say that either the positive direction is either up or down. I like to say that it's in the direction of acceleration just because I don't have to remember to plug in a negative number for the acceleration. But I'll show you what I mean by plugging in a negative number. So let's say that this is downward. So I'm still calling up positive, all right? So we get net force is equal to mass times acceleration. Because I'm calling up positive, I have still normal force minus the force of gravity is equal to mass times acceleration. Now, again, I'm solving for normal force here. So I get mass times acceleration plus the force of gravity, all right, which again is mass times acceleration of gravity. But when I plug in numbers here, I have to plug in a negative for my acceleration. So mass was 70 kilograms times acceleration, which is now a negative 4 meters per second squared, plus mass 70 kilograms times 9.8 meters per second squared. And so we end up getting 70 times a negative 4 plus 70 times 9.8, and we get 406 newtons. And again, dividing this by 9.8 will give us the mass apparent at the top, which is 41.43 kilograms. So you feel lighter at the top because your acceleration is downward. Remember, that floor is almost falling out from under you, so it's not pushing on you as much, and therefore you don't feel as heavy as you normally do. Now again, I called down negative this time. You could also call down positive because that's the direction of acceleration, but if you did that, that would make your normal force negative and your force of gravity positive, and then your acceleration would be positive. So you would get the same number if you did that. It works both ways, remember, as long as you keep your signs consistent.